Hello everyone. We're going to finish off the course with a couple topics regarding your favorite thing from Calculus 2, power series. So I say that in a facetious way because I think, we all really need to revisit power series to have a full understanding. Here's our definition. I added each C sub I as an element to the reals. Don't make things harder than they are. A power series really is just an infinite polynomial. And you can see examples of them here that we're going to express as elementary functions momentarily. But we're going to deal exclusively with a equaling 0. A is just a constant. It's really just a horizontal shift. But when a is 0, it makes it a little bit easier. But you can see that it's just an infinite polynomial. This is a number like the 1, and plus then C1, that would be like this 3, and then times x, and C2, that would be this 3 squared over 2 factorial, then times our x squared, and so on. It's an infinite polynomial as a power series. And you might recall from Calculus 2, the beauty was that we could express any power series. We could take any function, that is, and turn it into an infinite polynomial, that is a power series. And so I want to mention patterns, but before I do, there's some common power series on our table, the Laplace table that we've used exclusively for this 5th exam, which is our final exam. In the very lower right corner, I copied and pasted literally some of the common power series that we'll be dealing with. So you can see e to the x, formally defined as the sum as n goes from 0 to infinity, x to the n over n factorial. In expanded form, when n is 0, you'd have x to the 0, which is 1, over 0 factorial by definition, which is 1. So 1, when n is 1, you get x to the first over 1 factorial, which is 1, so just x. When x is 2, you get x squared over 2 factorial. There it is. And when n is 3, x cubed over 3 factorial, and so on. So these you're going to have to reference. And to talk about the patterns. The pattern is that you need to get used to. The fact is that a power series must start at 0. You cannot start at any other number but 0 in a power series. And so the values of n, in terms of the patterns, let me just kind of show all the different cases here. If you just have the natural pattern of 0, 1, 2, 3, and so on, in the summation expression for the power series, you're just going to use n, because that's the natural pattern. 0, 1, 2, 3, etc. If you have the pattern of, let's say, 1, 2, 3, and so on, then for that situation, it's really just a shift of 1 unit. That is, when n is 0, the value is 1. When n is 1, the value is 2, and so on. So therefore, we're going to just shift it by 1 unit and call it n plus 1. And then we have the need to recognize a pattern of even numbers. Let's say starting at 0. So 0, 2, 4, 6, and so on. Then we would use in our summation expression, since they skip, it's not going to be n plus 2, because that wouldn't work. Because if n is 0, it would be 2, and n is 2, it would be 3. n plus 2 is really a shift by 2 units. It would be 2, 3, 4, 5, etc. It's really a skip. So when n is 0, it's 0. When n is 1, it's 2. When n is 2, it's 4. Notice it's twice the amount. So therefore, we're going to use 2n. Okay, and then the odd numbers. 1, 3, 5, 7. And there we would use, okay, it's actually a combination of a shift and a skip. So you're going to use 2n plus 1. 1 to get the shift, to start at 1, and 2 to skip every other digit, every other number, integer. Okay, so I wanted to go over some of these examples before we get into the actual solutions. These are kind of just prepping us up for the situations we're going to encounter. And what we have to do is express each of these power series in terms of elementary functions. Because what we're going to end up with in our solutions to these differential equations are power series that look like what we're about to encounter. But we want to give them as elementary functions. In other words, either like e's, cosines, sines, hyperbolics, whatever, okay, any of these. We won't go beyond this set of elementary functions that's on your Laplace transforms table. So when you look at an expression, I usually focus on the denominator because that reveals quite a bit about the series. For example, if you look at the denominator here, 1, if you could actually put a 0 factorial, get in a different color here, but you could actually put a 0 factorial underneath this if you really wanted to. But if you look at the denominators, it follows the pattern of 0, 1, 2 factorial, 3 factorial. So look for that in the denominators. You see it right away here. But let's just glance. Do we see any others? No, these skip. Those are odd. Those are even. These are odd. These are 1, 2, 3s, but they're not factorials. So that's not it. Looks like the only one would be the e. And it is a sum, and that's what we have here. But we've got this 3 in the way. But notice that the power on 3 matches the power on the factorial as well as the power on x. That is, that's 3 to the first, x to the first. And you could really write this 1, if you wanted to, as 3 to the 0, x to the 0. And so this expression you can consider to be of the form 1 plus, and then what I'm going to do is I'm going to write this, I'm not going to worry about the 1 factorial. I'm going to rewrite it as 3x as a quantity to the first. And then plus here, I'll write this as 3x as a quantity squared over 2 factorial. And then plus 3x as a quantity cubed over 3 factorial, and so on. So by writing it in that fashion, you could see that it's really an expression that came from e to the x, but where each of these x's represent the quantity 3x. So in summation notation, you can write this as the sum as n goes from 0 to infinity of, instead of x to the n over n factorial, you could write it as the quantity 3x as a quantity to the n over n factorial. And then we certainly at that point realize that it's really e to the x, but where x is 3x. So as an elementary function, this would be e to the 3x. Okay, so then the next one. Kind of interesting here. We get the same situation in terms of the factorials in the denominator, but they alternate. Plus, minus, etc. And the powers are also 2, 4, 6 instead of 1, 2, 3. And so, therefore, when you look amongst this list, okay, we have to satisfy the factorials is probably the best thing to look for first. So the only ones with 1, 2, 3s is the e. Okay, look at all the others. They're either even or odds factorials. And this one, as we noted, it is not factorial. It's just the numbers 1, 2, 3. So this has to somehow come from e. Now, a couple things that are an issue is the fact that they alternate. The signs alternate. And then the powers, instead of being 1, 0, 1, 2, 3, it's 0, 2, 4, 6. Okay, so don't forget up here the patterns for 0, 2, 4, 6. We can use 2n. And the way to deal with the with the alternation of sign is to consider this as 1 plus a negative x squared to the first, and then plus a negative x squared over 2 factorial, and then plus a negative x squared cubed over 3 factorial, and so on. So you can see how by writing it in that form fits the form 4e to the x, because you have your 1 plus this quantity is now the x to the first, plus the quantity again squared over 2 factorial, and then the quantity cubed over 3 factorial. So notice how, naturally this took care of the alternation of signs. Negative 1 to the first is negative 1, negative 1 squared, positive, negative 1 cubed, negative, and the x squared took care of the fact that it's really 2 to the n, rather than just, or it's really 2n rather than just n in terms of the pattern. So in summation notation, you can write the sum as n goes from 0 to infinity. It's still going to be the n factorial in the denominator, but now in the numerator, a negative x squared as a quantity to the nth. And that's the same form for x to the n over n factorial, where x is negative x squared, and that's for e to the x, so e to the negative x squared. Okay, a couple more. Now we've got even factorials in the denominator. So let's look at the table. Even factorials. Okay, here's some even factorials, but these ones will alternate sign. What does ours do? A little video malfunction there. Okay, so what does ours do? These alternate signs. Ours are all positive. So probably disregard that one for now at least. These are odd factorials. Oh, here's some even ones. Okay, here's some even ones with positives. That's good. Let's check the powers on x. Well, look at this. X squared, x to the fourth. That's what we got. X squared, x to the fourth. Okay, and we got the even factorials, so those are taken care of. Powers on x are taken care of. Here's the issue, these 4s. But I can't absorb a 4 into the x squared. But I can rewrite 4 as 2 squared to get that common power, and then absorb the 2 with the x as a quantity squared. And similarly, this 4 squared I could write as 2 to the 4th, and then it'll match the power. And the 4 cubed as 2 to the 6th, and then the power matches. So this can be modified by writing it as 1 plus, here, let me do it in 2 steps. 2 squared x squared over 2 factorial plus 2 to the 4th x to the 4th over 4 factorial plus 2 to the 6th x to the 6th over 6 factorial, and so on. So now it would be 1 plus, now let's write this expression, kind of like what we did initially with the 3x, right? When these things matched, we were able to write it as a quantity to that power. So 2x is a quantity squared over 2 factorial plus 2x is a quantity to the fourth over 4 factorial plus 2x is a quantity to the sixth over 6 factorial, and so on. And now let's look back at our table, and we were focusing on the hyperbolic cosine here, and looks like everything matches now. We got the 1, got a quantity squared over 2 factorial in the form of 2x squared over 2 factorial, quantity to the fourth over 4 factorial, that's what we need here, quantity to the fourth over 4 factorial, and so on. So as an infinite sum, this is the sum as n goes from 0 to infinity of, and now we have the quantity 2x, but notice the pattern is 0 because there's really a 2x. If you wanted to literally write 2x to the 0 here, right? Really a 2x to the 0 right in there. So the pattern's 0, 2, 4, 6, etc. So that's to the 2n power, because it's even. And then over, and this is almost given to you within the context of the formula, because it's, you see it, it's x to the 2n over 2n quantity formula, quantity factorial. I'm just trying to build it without having to consider that. And so, as we see, that's for hyperbolic cosine of x, but Rx is 2x, so therefore hyperbolic cosine, or the cosh, of 2x. Okay, so then for a final example here, now we've got some odd factorials and some sums. So, the odd factorials. Here's one here, but the signs alternate. So here's one here, and the signs are all positive. Alright, so that's a good thing. Let's check the powers on x. So we're looking at the hyperbolic sign here. What are the powers on our x? Oh, nice. First power, third, fifth. That's what we got. First power, third, fifth, seventh, etc. But then there's the issue with the fours again. So, we'll take the same approach initially as the previous problem. That is, I'll write this as x plus 2 squared x cubed over 3 factorial plus 2 to the fourth x to the fifth over 5 factorial plus 2 to the sixth x to the seventh over 7 factorial, and so on. But at this point, there's a little trick, because we have to have this such that, let me get rid of this equals for now. I'm going to do a little trick in here. Put the equals there for now. We have to have it such that the powers on the 2 match the powers on x, so we can absorb it and write it as a single quantity raised to a power like we did in the last example. Notice that they only differ, the powers on 2 and the powers on x, by 1 factor. That is, if I had one more factor of 2 here, that'd be 2 cubed, and that would match the power on x. If I had one more factor here, that would be 2 to the fourth, or 2 to the fifth, and that would match the power on x, and so on. So therefore, if I just multiply everything by 2, I think I've got it. But if I do multiply by 2, so that's why I left a little space out in front, I do plan on multiplying this by 2, and this one by 2, I'm distributing the 2, and that one by 2, and everything by 2. But if I multiply by 2, I have to compensate, so I'm going to put the whole thing in a big set of parentheses. I'm going to compensate by multiplying outside by 1/2. So then this becomes 1/2 times the quantity 2x to the first plus, now, here, let me show it like this. Let me show it in 2 steps. This will make it more clear even. 2x plus, now this will be 2 cubed x cubed over 3 factorial, and then plus 2 to the 5th x to the 5th over 5 factorial, plus 2 to the 7th x to the 7th over 7 factorial, and so on. Alright, so now let's write it. 2x quantity to the first, plus this will be 2x as a quantity cubed over 3 factorial, plus 2x as a quantity to the 5th over 5 factorial, plus 2x as a quantity to the 7th over 7 factorial, and so on. Which, as an infinite sum, is, well, we've got the 1/2 out in front. And then as an infinite sum, what's in brackets, always starting at 0 to infinity. Okay, they're following the pattern of 1, 3, 5, 7. That's the odd numbers, so 2n plus 1. So without looking at the cheat sheet yet, I'm just going to try to do this with a firm understanding. Odd powers, 2n plus 1 over odd factorials. There's really a 1 factorial under this 2x. So 2n plus 1 is a quantity factorial. So that's 1/2 times, now the elementary function, let's go back. We were looking at the hyperbolic sine, it was, right? That matched everything. Here, let me slide this under here so we can line it up and see it. Okay, so the hyperbolic sine was where the x was 2x, the x cubed, 2x quantity cubed, 3 factorial, and you can see everything matches. And look at the summation, x to the 2n plus 1, 2n plus 1 quantity factorial. So don't forget we had the 1/2 out in front, and now that summation becomes the hyperbolic sine of x, but where x is 2x. So therefore, hyperbolic sine of 2x. Okay, so I wanted to go over those because I wouldn't want to really spring that on you, all of that concepts on you within the context of or solutions to these differential equations by the power series method. I'm just going to talk about the method and the theorem, and then we'll come back and look at some examples in the next part of this video. But some of the theory is that we're going to assume that the power series, just your basic power series, c sub n x to the n, as n goes from 0 to infinity, just assume that it's a solution, okay, to the differential equation. And then we're going to find these constants, C0, C1, C2, and we'll have an infinite polynomial. And then we're going to be able to express as an elementary function like we just did. The first theorem is for derivatives. If you consider the function f of x to be equal to the sum as n goes from 0 to infinity of c sub n x to the n, this is the expansion, c0 when n is 0, c sub 0, x to the 0 is 1, so just c0, c sub 0, n is 1, c sub 1, x to the first, c1x to the first, c1x, n is 2, c2, x squared. Okay, so that's the infinite series that we're assuming is a solution. If it's differentiable on I, if it converges on I, then f is differentiable on I, and this is our expression for the first derivative. Now notice that the index changed to a 1. And it's almost like we took the derivative of this c sub n x to the n by swinging the n down in front times c sub n times x to the power 1 less. But notice how the c sub 0 is gone, and it's just c1 plus 2c2 plus 3c. So it's like we took the derivative of each of these as well. Because derivative of this constant 0, derivative of this is 1, derivative of this swing down the 2, c2 x to the first, and then the next term would have been 3c3 x power 1 less 2. Well, here's the proof as to why that's true. If you start with f of x equaling, let's say, c sub 0 plus c1x plus c2 x squared, I'm going to throw another one in there, plus c3 x cubed, and so on, which is the sum as n goes from 0 to infinity of c sub n x to the n, then f prime of x is going to be the derivative of c sub 0 is 0, derivative of c1x, c1, here the derivative of 2c2 x to the first, power 1 less, here swing down the 3c3 x squared, power 1 less, and so on. But then that expression can be expressed as, just looking at that expression without looking at the summation, just looking at this expression, it can be expressed now, instead of starting at 0, starting at 1 to infinity, of, we're going to need the value of n, because n is 1, 2, 3, and so on. So we're going to need n, c sub n, but then it's x2, to get just a constant here, if the index starts at 1, it would have to be the n minus 1th power. Okay, so that's a quick proof as to why this is true. So basically, for our purposes, we're going to be dealing with, as we'll see in the next page when we do an example, we're going to be saying that y equals the sum as n goes from 0 to infinity of c sub n x to the n is a solution. It's the same as saying f of x. I just want to point this out. So then we're going to say that y prime is the sum as n goes from, important there to understand y, and we showed it here, the index changes to n equaling 1. And then it would be just like you're differentiating this piece normally. Swing down the n, c sub n's a constant, x power 1 less, n minus 1th. Okay? Alright, so we got a couple more theoretical things to talk about, and then we'll get to an example, and we'll take care of that in the next part of this video.